Good afternoon. Welcome back after lunch. Have you heard recently that there is a new discovery in human brain? It's a very much controversial topic worldwide. Neuroscientists from all where are puzzling with this. So there is discovery of a new meningeal layer in human brain. You must be knowing that our brain has traditionally we describe the three coverings, the dura mater, arachnoid mater, and the pia mater. And this information we know before, this has been known to us before the arrival of the Christ. This knowledge is from BC, from the times of Aristotle and Herophilus. So after hundreds of years, so there is this claim for the discovery of a new meningeal layer. Primarily, this data has been from the mice, but a small bit, authors also provide evidence from the human brain. The paper was published in January 2023 in Science, and it has created much uproar. We have also got into that. Initially, we are surprised how something can be discovered in the human anatomy like that. So we reviewed that data and wrote some letters to the Science, and they were rejected. Many other scientists groups wrote letters, and they were also rejected, and they received some not very pleasing response from the original authors against their e-letters, which were published by Science as e-letters, but not in the original, the print publication. The e-letters anyone can publish. So there was a huge discontent over the discovery. We started investigating in the human brain. We are working since January 2023. We have the enough original data for now. Here we are not. I am not presenting here the many original data because we are yet to publish. Recently, we published in the Anatomical Records, very prestigious human anatomy journal, not human anatomy, anatomy journal, all anatomy. So we had a question because a meningeal layer is a macroscopic structure. So it should be externally visible with naked eyes. So why we didn't see this? And for many centuries, why others could not see? So we wanted to revisit the literature that anyone has described this layer in any form. And starting from Kian Regius, in 1875, who first described the anatomy of the subarachnoid space and CSF circulation in subarachnoid space. First description was given by the Kian Regius. That got ignored. Later, many tried to recover that information. That was also not, means that didn't create much interest in the people and got ignored. So we found almost 7 original descriptions that in some form an intermediate leptomeningeal layer in the brain was previously described. Intermediate leptomeningeal layer means we call the arachnoid and pia together as the leptomeninges, the soft meninges. Dura mater is the hard meninges. In between that, an intermediate layer was described in some form. Here I will show you, we relabeled those images, some of those images, and that has been published in the Anatomical Records. And we have also included a few of our original data. So what is relevant here? But while checking the presence of this meningeal layer in the human, we got trapped into an evolutionary question. So the Science paper, the main data was from the mice. In the Science paper, the data was from the mice brain. And what we see here in the human, something is opposite of that. We are able to we are able to make out an intermediate leptomeningeal layer Even in details we'll publish soon. But there is some evolution here, means everything in the mammals should be, at least in the mammals, should be conserved. At least the basic plants should be conserved. How anyone can expect that there is means gross mismatch between the mice brain and the human brain? So let's start. I will be showing data one by one. So this structure, the new meningeal layers, the authors named as the subarachnoid lymphatic-like membrane based on the immunophenotypic expression. They showed that this layer is immunophenotypically distinct from the arachnoid matter as well as pia matter. So in brief, we will call it SLIM. And this layer is dividing the subarachnoid space in the two parts. And this layer is impermeable, means it cannot give passage to the particles more than 1 micrometer and 3 kilodalton weight. So means CSF space is bipartite, two functional compartments it has. This discovery is establishing that. But I already talked that the discovery got into controversy, and controversy is still going on. So here, this is a schematic diagram from my own paper. Is it working? I think it's not working. Here. Okay. So here, this in green, you see a layer that is dividing the subarachnoid space. We'll call it the SAS now, in the two parts. And the inner compartment, you see the vessels. So the original authors in the science, the Molgaard et al., and they are the group from the University of Copenhagen and the University of Rochester. So they told that this inner compartment below this green membrane is the vascular layer. Here is the vascular network you will find. Okay, so this is very relevant to us. We will come to that soon. Okay. So they checked this in the mice using the 2-photon microscopic living mice. Mice was PROX1 GFP transgenic mice, and PROX1 that is expressed in this green membrane, the SLIM. So they used that as a marker, and you can see the vessels are beneath that green membrane. So inner compartment is the vascular compartment mainly. Next. Further, they used the CSF tracers, and they showed that the tracers could not pass this layer. So you can see the different color tracers are specific to the compartment. They are not passing easily. Okay. And they showed that this layer is immunophenotypically distinct. So they performed a lot of the immunohistochemistry also. We are not going into the detail that. So what we did, we systematically reviewed the existing literature that I described to you, and we published that now in the anatomical records, and we are ready to submit now the original data also from humans. That I am not mainly presenting here. So first I am showing you how this membrane is present in the mammals. So labeling us are from our publication, and these are the historical pictures we relabeled. So here, the original authors, so this is the brain part, and the pia mater is a single layer membrane. So it's always adhered to the brain surface. So if you try to separate that, it will break. So original authors of this paper had labeled pia mater this. We have relabeled it here. And this is a thick membrane. So all the fluorescent markings are from us. This is the arachnoid matter, this is arachnoid trabeculae. So we really labeled this thick membrane, the collagenous, and it has the cellular layers also, as the SLIM. It's our own assumption. So then there is two compartments. So So this is the scanning electron microscope from the mice brain. We have similar pictures now from the human brain. This is the dog brain again. The original authors had labeled this structure as the pia, okay, but we are relabeling this as the pia is the single cell layer thin membrane. So histologists will be familiar with that. The thick membrane cannot be pias. Here is a thick membrane attached with the arachnoid trabeculae. So this is the slim. Actually, what happens is the fixed brain, fixed tissue, the layer, the CSF is removed, the space gets collapsed, then layers get adhered to each other. And this adherence is always irregular. Somehow it will be separate, somewhere it will be totally adhered. So this we propose as the new meningeal layer, the subarachnoid. So again, you can see here that this vessel is above this. Means this vessel, the large vessel, is in the outer compartment. So this is our question of the evolutionary question. We will come to that later. Again from the dog brain, the original authors had labeled this the pia mater. Here they had correctly labeled. So this one is the pia mater, it's correct labeling. But superiorly above, this one is the hanging layer is the new layer. And above that is the arachnoid mater. So same layer here, it's a pia mater. It's a original labeling pia mater. So it's from dog brain. Again, this picture is from the representation of the rat brain. So 10, transmission electron microscopy. Here, the Chris et al. In 1983 had first proposed the compartmentization of the subarachnoid space. So there is historical evidence. So their original picture, we have just color marked that. So this is the outer space arachnoid, and this is the inner space. So this can be the external pile layer, the named is the new meningeal layer slim. So this picture has been presented as an evidence by the science authors also. They also redrawn this picture in their support. Again, here a representation of the TAM from the mammalian brain and a histological picture. Both have been measured, and this histological picture is so accurate that every structure, even the fibroblast, you can mark it as a very resemblance, accuracy of the TAM. So here the above dura, arachnoid layer, these are our own labelings. Here is a fibroblast near to the brain. We say the pia. This layer, these fibroblasts joining each other, what are they? The original authors had missed to label that. We say that this is the intermediate leptomeningeal layer slim. Okay. So similarly, here is also in the HNE imaging, this layer. Pia is here, is originally marked. It's original labeling. So this is matching with this. Pia must be closer to the brain surface. It's adhered to the, you cannot remove the pia from the brain. So again, so here is this one will be the outer compartment between arachnoid and slim. This is inner compartment. Both have vessels. But see in the picture from the pig brain, a large vessel is in the outer compartment. I repeatedly showing the position of vessels because we will be discussing that very soon. Again, this is a case of the benign enlargement of the subarachnoid space in infants. We tried to look into with our radiologist from AIIMS Patna that can it be seen from in the MRI images. So no, in the healthy adults we couldn't find, especially in the brain part. But in this peculiar case of the base, benign enlargement of subarachnoid space, a disease where subarachnoid space is very much enlarged. So here you can see a faint membrane line dividing the white is CSF space into two parts. From where that came the faint line? That's not vessels. When I discussed with our radiologist, that he told that probably you are true. So we always ignore this. It may be vessel or just we ignore this. So, but in normal healthy individual, where the CSF space is very much narrow, you will not see this. But if from the normal individual, I am showing you now the T2 MRI images from the spine. The largest cistern, the cisterna magna, starting from there, a thin layer, somewhere getting wide, is dividing the subarachnoid space in the two. It's a faint blackish. So can you see it with the more advanced MRI, like the 7 Tesla, 9 Tesla? Recent one is 11.4. No. There the CSF space you will see is so much hyper intense that you cannot see anything except the CSF. So maybe the company persons will need to redesign that. There was no knowledge of this meningeal layer, so there was no need of seeing this. If they readjust something, technically maybe. Because in the 11.4 Tesla, you can see the brain like a resolute histology picture. Optical coherence tomography. This is picture by one of the slim opponents. They opposed with this picture and relabeled it and shown them that in your picture there is an additional meningeal layer. That is here. This is arachnoid, pia should be near to the brain, this thick layer. So connected all where? Transversely. Complete layer. So there is formation of two compartments. Again, this is from the MRI, image from the very recent paper in Nature. They came as in support of the slim, not very confidently. What they did, they pushed some CSF tracers in the subarachnoid space and followed that with the contrast MRI. They showed that around the arteries there is a perivascular halo, enhanced perivascular halo with time. So that's the CSF tracer is shown. So how that CSF reached there? So there is perivascular sheath. Again, this perivascular sheath can be made of the either arachnoid or pia. So these two layers make the boundary of the subarachnoid space. If they make the sheath, they can make sheath, but they cannot enclose CSF within because these layers are at the boundary. How come the CSF entered in the perivascular sheath? So they, okay, thank you. I will be finishing soon. So they play the logic that there must be some intermediate leptomeningeal layer. So now I have to finish within the 5 minutes. So I will go fast. So I will discuss my evolutionary question now. These are clinical data from our own departments. We'll miss that. So what